Okay, I think we have a good quorum of people, so we might as well get started. I will very quickly kind of say a few words and then turn this over to Nate, who's going to be running the webinar for us today. So I'll just say welcome everybody to a new reincarnation of the IR STIG webinar series. We're trying something a bit new this year, which is instead of having sort of the longer hour talks that we had before, we're trying to really infuse the science and technology together. So that means that going forward, starting today and through the rest of the series, we'll have 2 talks per session. One of them will be more technology focused and one of them will be more science focused. And I think this will be good to sort of get more discussion going amongst our group. So with that, I think I'll just turn it over to Nate, and thanks everybody for joining.
All right, so I'll go ahead and I'll introduce our first speaker today. We have Dr. Jason Austermann presenting far infrared kinetic inductance detectors at NIST-Boulder. Jason is a physicist at NIST-Boulder with over 20 years of experience in the development of cryogenic power sensors, optics, and readout. Jason's work spans a large range of CMB and astrophysical experiments, typically working in the millimeter and the far infrared. So with that, I'll go ahead and stop sharing and hand control over to Jay.
All right, Chair. Hello, everybody. Thank you to the committee for giving me a chance to talk to you all here, and thank you for coming. Can everybody see my screen all right? Take that as a yes.
It looks good, Jay.
I turn on the laser pointer here. I haven't used that before, but I wanted to try it. All right, so yeah, my name's Jason. I'm at NIST-Boulder here. I'm part of the quantum sensors group. There's a picture shown in the right here. We have quite a large group. There's a large range of projects here, ranging from high energy calorimetry to cosmic microwave background work, many different types of detector technologies, readout development, cryogenic development. So this is a really large group, but an outdated picture. Only a very small subset of us work on kinetic inductance detectors here. In fact, you could count them on one hand. But I just wanted to give you a context of our group here. So I know this is a mix of science and technology nerds, me being more on the technology side. So I wanted to make sure we're all on the same page. So I'm going to start with some very basic context. So here's the atmospheric transmission from a very good site on Earth, in this case, Mauna Kea, on a very good weather day. This is from the CSO atmospheric modeler, ranging from 100 gigahertz to 1.5 terahertz, or 3 millimeters to, 200 microns. So I'm not sure what you all would consider far infrared, but in my mind, the clear divisions where the atmosphere goes bad and things become really hard from the ground. And so I'm going to talk about our technology that's been developed and is applicable to both. I just wanted to make it clear when I say far infrared, that's what I mean. The other point of context here is what is a kinetic inductance detector. So I'm going to start off with what it isn't. So here's a simple picture of a classic bolometer, in this case, a transition edge sensor bolometer that you may be more familiar with. So you basically have a dangling heat capacity that has a very weak thermal link to a thermal bath. Even a small amount of power dumped onto it, in this case, input radiation from your telescope, will heat up that heat capacity, maybe as you scan across a planet here. In the bottom left, you can see resistance versus temperature. If you're biasing, say, a superconductor right on its transition, it'll be very sensitive to even the most minute changes in temperature. And if we track that change of resistance, say, via the current through the device for a constant bias, you get a response something like on the right. Bottom right, as you scanned across the telescope, as this thing heated up and then cooled back down. That's not what this is, but just wanted to give you some context. So kinetic inductance detector is an athermal device. So there's no thermal processes going on here. And you'll often hear different acronyms for kids. You'll hear just KID. From my group, you'll hear a lot of MKID, so microwave kinetic inductance detector, or the microwaves, how we read it out, or a LAKID for a lumped element kinetic inductance detector. There's also a fourth kind you might hear, TKID. That's actually a thermal version of this. It's actually more like the picture on the left. And we do dabble in that here, but I'm not going to talk about it here because its use cases are more in high energy and stuff like that. So here, this is an athermal device. So on the right, I have this little gray superconducting circuit sitting on top of a thermal bath, with the charge carriers shown in red and blue circles there. So if it's a superconducting state, most of the electrons are bound into Cooper pairs, which produces the superconductivity effect. But input radiation, if of sufficient energy, can break some of those Cooper pairs, changing more of these Cooper pairs into free electrons. And since electrons and thus Cooper pairs have mass, they have momentum. So in an alternating circuit, this will actually change the kinetic inductance of the device. So since they have momentum, they induce an inductance in an AC current. And so in this sense, what you'll see as a signal is if it's in a resonant circuit, you'll see the resonant frequency change as the inductance of the circuit changes. And the bottom right is just kind of a cartoon representation of what the inverse frequency would look like, which is your signal as you may scan across the source there. So it's a very simple cartoon view of what a kinetic inductance detector might do. Further for context, just wanted to talk a little bit about noise equivalent power, or sort of the noise limits that are in effect here. So what your sensitivity of your detector is. So ultimately, the function of any power sensor is to transduce the input power signal to a calibrated electrical signal with minimal added noise. So the right plot is what a photon noise limit or background noise limit, a function of total incident power. This is the minimum noise incurred for any measurement due to the random arrival of photons in the thermal source. So you can't do really better than this. So you can see that fundamental noise floor of the measurement itself is a function of not only the total incident power, but kind of the band or the frequency or wavelength of the photons that you're looking at. And there's both a shot noise, a random Poisson kind of term, as well as a photon bunching term at really high powers. That's why I see it turn up kind of at the high power end. So this is the fundamental floor. So why do we want to use superconducting sensors to do this? Well, we want to keep the sensor noise below this fundamental noise, so the detector is not adding a lot of noise to your measurement, and you're dominated by the measurement itself. Superconducting sensors help us get there, one, by driving down the thermal noise. So by definition, superconducting sensors work at cryogenic temperatures. So you're driving down, if you work at very low temperatures, you're driving down the available thermal energy states that can couple to your sensor as noise. Also, for a superconductor, allows you to access kind of quantum limits, as superconductivity is a quantum effect. So at this level, the photon energy becomes important relative to the thermal state energy. So if we can drive down that KT relative to H nu, you're generally going to win. There's additional benefits of superconducting sensors. They're generally going to be low loss because there's no resistance. It kind of helps you develop new and novel signal transduction options. So transducing that input signal to a readable electrical signal. It's very enabling for readout, and especially in a sense of reading out hundreds or thousands of detectors on a single readout line, which is what you need when you want to start talking about tens of thousands or more of detectors. So here again is that photon noise limit. It's kind of as a function of the input power and your photon energy. And then I have listed here just kind of the fundamental noises of two prominent kinds of detectors. So it's the TS bolometer, which is kind of driven by the thermal properties of the device. So it's kind of and on the MKID, it's driven more by the recombination noise of those when you break Cooper pairs into electrons. The randomness of them recombining in the Cooper pairs is a source of noise, and that's the fundamental noise of that source. But in the end, to zeroth order, they kind of are the same fundamental limit. So your signal limit is the power and the is related to H nu, the energy of your photon, while each of the fundamental noises of either an MKID or a TS bolometer is kind of driven more by KT. So again, driving down that temperature gets you to that fundamental limit of the detectors. So if we keep KT below H nu, you're generally going to be subdominant in your detector noise relative to the signal noise. So this is all just to kind of say that MKIDs are competitive with TESs. And in fact, a very recent paper by some of our colleagues out in Europe have developed a kinetic inductance detector with a noise floor quoted at about 3 × 10⁻20 watts per root hertz. So it's a new kind of record of a new noise floor. So again, showing that very low noise floors can be demonstrated with these kind of detectors, which would make them applicable for some of the future space-based and balloon-borne kind of far IR experiments that are being devised. So again, this kind of shows us why They can be competitive with TSs, but I want to point out some reasons that will drive you to an MKID versus a TS bolometer. There's several here. One, that you can make these without a membrane. So they can be just right on a hard, thick substrate of silicon. It makes them very mechanically robust, whereas a TS bolometer is generally that thermal island. Shown in the upper right here is one of our TS bolometers at NIST. It's just suspended by these 4 legs, and everything else is open space in the black. So it's just the little membrane kind of flapping in the wind if you accidentally let wind in there. So they're not mechanically robust, although as a community we've gotten very good at using these things and keeping them intact. But if you're going to drive to very, very low input powers and noises and very high sensitivity devices, these legs are going to get even longer and more complex, and the devices themselves are going to get more fragile. And that's kind of where there's a win for kinetic inductance detectors, and they're very mechanically robust. Also, they're oftentimes, not always, simpler to fabricate. So in the examples I have shown here in the photographs of an example TS and an MKID detector, the TS has something like 5 lithographic layers just in this image alone, as well as a couple different silicon etches. Whereas the kinetic inductance detector could be 1 lithographic layer and maybe 1 deep etch from behind to form a back short or something like that. So much simpler fabrication that can be beneficial, especially when scaling to a large number of devices. There's also no strong saturation limit to a kinetic inductance detector. So here again is the TS bolometer kind of resistance as a function of temperature. So you generally operate, in the middle of a superconducting transition, going from no resistance to its normal resistance. And at some input power level, you're going to drive it normal to its normal resistance. It's going to have very little to no response left. So there's a limit to how much power you could dump on that detector before it becomes useless, or extremely noisy at least. For a kinetic inductance detector, I have plotted here, this is 1 detector. So if you remember, if we build it as a resonance, this is the same detector resonance, but at different input powers of light onto it. So as we dump more power, its kinetic inductance goes up and it shifts to lower and lower frequencies. Its amplitude also goes down, but I'm spanning here about 3 orders of magnitude of input power, from 0.2 picowatts to here 131 picowatts. And over this entire range, not only is the device operable, but it's near a background limit for what it was designed to use over these power ranges. So there's a very large dynamic range possible with kinetic inductance detectors without a saturation. This can be very important. 2 smaller pixels can be possible, especially as we start thinking about extremely sensitive, low power devices. Again, like I mentioned with the mechanically robust comment, TS are generally get more complex legs, longer legs, and have some sort of finite dimensional quality to them as you drive in that direction. Whereas a kid actually naturally wants to get smaller as you go to lower powers. We want to drive the volume to lower volumes to make it more sensitive for those low power states. So it's kind of a natural thing when we want to go to very sensitive devices and to small devices. And finally, and this is the most important in my view, the device itself is inherently multiplexable. And that is, you can read out hundreds of thousands or thousands of these devices on a single readout line. So it's effectively integrated circuitry. And I'm going to go into a little bit more detail on this, because as someone who not only works on developing detectors, but also designing assemblies and doing the assembly work, it can be a lot of work when these assemblies get really complicated. So how do you read out a bunch of MKID resonators? So as I mentioned, the kit itself, you have a variable inductance that depends on the amount of power dumped onto it. You put it into a circuit with a capacitor that makes an LC resonator that resonates at a specific frequency. You can put a bunch of these on a single feed line, microwave feed line, and then read them all out simultaneously. So here is an array of about 500 devices. Each one of these little spikes is a different MKID detector between roughly 450 and 900 megahertz in this case. So basically we can fit like 500 to 1,000 typically of these devices within 1 octave of readout in these kind of 500 megahertz or gigahertz kind of range that we typically read these things out at. And all of this readout multiplexability can be done on the same wafer, in the same lithographic step that define the detector itself. And so this is a comparison I like to show of projects that I work on, both on the TS side and the KID side. So on the left is sort of representative of recent state-of-the-art TES project. This is from Advanced ACT Poll. So in the center, you're looking at the back of a TES array of around 2,000 detectors or less. And these are polarimetry sensitive, both sides. But then you see that all the integrated electronics around it are required to read out these 2,000 devices. And I said integrated, but they're integrated by hand. They're not integrated in the sense in fabrication. So all of these different devices you see out here, different squids and bias resistors and stuff like that. There's dozens of individual chips and cables, thousands of wire bonds that all go into this, many points of failure. We've gotten very good at doing this. And sometimes you'll see these in more modern projects like Simon's Observatory, where basically all this complexity is folded onto the back of the array. So it's more compact. You can put multiple of these together, but the complexity is still the same. This is just more folded out that you can see it. Very complex, tens of thousands of wire bonds and such. And so once you put this thing together, you're probably never going to take it back apart. And it's a lot of work to put together, but people have done great work. And these are very high performance devices. But by comparison, on the right is a MKit array for Toltec, and it's about 4,000 detectors, so twice as many detectors, but the whole thing can be assembled with only 14 wire bonds compared to tens of thousands. No additional silicon or fabricated chips, just one commercial PCB, and then 14 coax cables here. And that's it. So it's very quick to put together, very simple, and very practical if we needed to take it apart and rework something. And that's the last point I'm going to get on this, is the rework ability of MKids. So one of the yield hits that you can take on kids, besides physically, they're almost always 100% yield, but one of the yield hits you can hit is that not all of the resonators fall at the exact resonant frequency that you designed, and some of them will collide. And if they collide, that can be a large amount of crosstalk. And basically, if it's too much, the device is unusable, so you lose both detectors that are crosstalking a lot. So here's one example of where we made an array of about just 100 devices. You can see some of the resonances are very close, maybe crosstalk, and some of them are more far apart. But because it's easy to go back and work on these things after measuring them, we can put these back in the fabrication and edit what the capacitor of that LC resonance and move each individual device in frequency space. And after that simple extra fabrication step, this is what that same array was measured as afterwards, and nearly every detector was perfectly spaced from one another. And the yield went from, I don't have the numbers here, something like 70% by a crosstalk criteria of a few percent to about 98%. So that was an interesting demonstration we did about 5 years ago, and just one of the many strengths of KIDS. All right, so that's a lot of background work there for the kids. And I just wanted to get into now more specifics about the devices that we do at NIST. And all this comes, the different types of devices comes forward from how you couple the light in. And so this is kind of a broad view of the different ways you could imagine doing it. You can do direct absorption on the devices shown in the bottom right, or kind of just a bare antenna, like a phased array antenna. Some experiments might use to bring the signal down to some sensors. In this case, TS is here. These are MKids I'll talk about in a minute. You can use micro lenses, or in the millimeter community, you might call these lenslets, to in a more traditional approach to focus the light onto the sensor and create more space for your ancillary electronics on the device. Or there's the classic example of feed horn and waveguide coupled. And then there's another project to work on at NIST, working on metamaterial lenses to basically focus the light at each pixel. I'm going to focus mostly on direct absorption and waveguide feed horn coupled, because that's the primary thrust of our KID development, with just a touch of metamaterial technology worked in. So first, I'll talk about our feed horn project. So there's a long heritage here beyond our MKID project. So even before that, we've done feed horns for a multitude of CMB projects and TES bolometer projects. But here's a span of what we've currently and recently done for MKIDs behind feed horns. So our first development was actually in the far infrared for blast TNG, working at 250 to 500 microns, 3 different arrays. Here's one of the blast launches there. Unfortunately, there was a mechanical failure on the telescope itself a few hours in the observation, so not a lot of science was done with it, but we did get our first test and first light of our kids on the sky, which was very exciting. These were actually behind metal feed horns, which I'll talk about in a second. Right now, we're commissioning the Toltec instrument on the LMT. It's there and being commissioned. Again, it is like blast in that it's 3 different wavebands, but now in millimeter, from 1 millimeter to 2 millimeter, and behind silicon feed horns, which I'll talk about in a second. We're currently doing a wide range of projects for CCAT Prime, which have a large number of optics tubes for different experiments ranging from 350 microns to 1 millimeter. So in essence, the basic way our kids behind a feed horn work is here. In the left is a cartoon cross section. The feed horn couples the light into waveguide. our absorbing part of our detector sits right below that waveguide. It's coupled efficiently to the waveguide and absorbs the photons, breaking the Cooper pairs, changing the kinetic inductance of the detector. The feed horn helps create area in the focal plane for IDC, for the capacitor to create the resonance, and feed line to connect all the detectors together and still efficiently use the focal plane area. On the right is a micrograph of one of our detectors. So there's two detectors per pixel in these experiments, typically, picking off each picking off one linear polarization state. So there's a vertical and a horizontal inductor and absorber, coupled each to its own capacitor, resonate at a specific frequency, and connected to a feed line here. So what I mentioned metal versus silicon feed horns, and this is an interesting thing we developed first for CMB projects, in that we can create just about any arbitrary feed horn shape we want, including incredibly complex ones you could never imagine really machining, out of stacking dozens of silicon platelets that each have a unique hole etched into them. You stack them up kind of like you've seen on the bottom right in cross section, and make a profile. And this profile can be optimized to whatever your experiment might be. It could be a corrugated profile or a wideband profile of different sorts. So this is kind of, in the upper right is an expanded view of many of these wafers of different hole sizes that will eventually be stacked and metallized into one continuous conductor feed horn shape. So we've done this a lot. This is just a couple of the large 6-inch kind of diameter arrays of thousands of detectors for Toltec. So these are, this is the 1 millimeter array on the left, 2 millimeter on the right. We've done this many times. We can measure this at room temperature. These are the cross-sectional beam profiles and the E and H planes. So two different polarization planes as you sweep across in one dimension. And basically the lines versus the dots just basically show, to the extent that we can measure it, these feed horns almost exactly match what we simulate. So using photolithography to define these feed horns to 1 micron or better features just allows us to create beams that are extremely precise and very uniform across the array. So those that I just showed were for the millimeter wave bands. So I'm working a lot to try to push this into the submillimeter and far infrared. So what that takes is making much finer etches and much finer holes and refining our commercial metallization and plating processes in there. So right now we've just made an 850 gigahertz CCAT prototype, set of just 5 feed horns here, and we'll be testing that soon. We've done test etches for Blast Observatory, the next generation of Blast, which will go up to a band of 175 microns. So basically, we're going to try to push this feed horn technology up to 1.5, maybe 2 terahertz, so that it can be very useful in the long wavelength end of the far infrared. I have developed a numerical optimization code to come up with the best, highest mapping speed, low systematic kind of feed horn profile for whatever your experiment demands. So as an example here for the Blast Observatory proposal, I optimized a new feed horn compared to the previous generation Blast feed horns that were machined into metal. And I was able to get a gain of 20% of mapping speed just from optimizing the feed horn profile and making these out of silicon. There's a whole lot. There's many other advantages to doing these out of silicon and many problems with far infrared stuff in a metal feed horn that I'd be happy to talk to someone offline about. You can do them out of metal, but it causes, there's more challenges. And finally, with the feed horn coupled stuff, I just wanted to do one quick little note, what we do with TSs, and we're trying to apply this to MKIT as well, and that's a multi-Croic pixel. So that's putting on-chip circuitry to couple the light to microstrip and then split the light into different bands. So you can imagine doing this as a spectrometer in many bands, but what we've typically done the CMB is split into 2 or 3 bands with a diplexer or triplexer. In this case, we have a photograph on the right and a diagram on the left of just splitting the 2 polarizations each into 2 different bands. In this case, 150 and 230 gigahertz. But basically, you can put microwave filters on there to split into 2 different bands, direct the light into, in this case, a TS bolometer. So we're currently working on being able to do this, but replacing the TS bolometer with a kinetic inductance detector. So that'll allow basically 4 or more detectors per device. Okay, so that's the feed horn coupled stuff. Now I wanted to go over quickly the recent project that we completed. Was a 6-month intensive investigation into a possible upgrade of the Hawk Plus receiver for SOFIA. Now, unfortunately, as we all know, SOFIA is being shut down, so that full upgrade project will not happen, but it did produce a lot of fruit here at NIST as far as new detectors and technology. It was very, very helpful to us in pushing the technology along. There's three major accomplishments here. We developed an on-chip metamaterial anti-reflection treatment that's integrated with the detector array itself. An all-new broadband FR detector using MKIDs that is extremely broadband because Hawk Plus goes 1 to 6 terahertz. So that's 6-to-1 bandwidth. That's something new that we hadn't done before. And developed quickly an all-new set of readout electronics for reading out hundreds of these devices per line. On the left is just an image of a prototype of 64 of these pixels. Very quickly, what on the left is the diagram of what these devices look like. So far infrared lights coupling from the telescope above. We backside illuminate the detectors in the sense that the first thing to see the light is the back. We etch a metamaterial anti-reflection layer into that to couple the light from free space into silicon, because that helps you with efficiently coupling to the light. Then it gets on the other side of the silicon to our absorber that absorbs and detects the light of the KID detector. Again, here's a picture of the 64 pixel prototype. And then it's all backed by a second wafer that produces a back short that helps enhance coupling to the light, coupling efficiency. Speaking a little bit more about the anti-reflection layer. So these are simply just very small etched holes into the back side of the detector wafer. We did develop both a single layer AR if you're doing a more modest band. We also developed a double layer AR where we etched 2 little sets of holes as the cross section, where you etch one deep hole at one radius and then one wider hole to an intermediate depth of the back of the wafer there. And this allows us to do a very broadband anti-reflection treatment for something like Hawk that was 6-to-1 bandwidth. And on the bottom here is pictured the transmission or the absorption efficiency of the devices in simulation as a function of frequency from 1 to 6 terahertz. You can see the 5 Hawk bands in color there. And basically the black line is our simulation of the efficiency of the full device with the double AR treatment, and blue with the single AR treatment. And both are very good compared to the original Hawk Plus devices that had a maximum efficiency of about 50%. We got all bands to be, at least in simulation, above 90% optical efficiency. I won't go into detail this, but long story short, we've measured the anti-reflection treatments with an FTIR, and they very well match our expectations from what was actually fabricated. So it shows it's doing what it's supposed to be doing, which is fantastic, and matches simulations. Here's what the detectors actually look like themselves. So in the center is the layout of a single detector. The large 80% you can see here that looks similar in the middle is the actual absorbing part of the detector that is sensitive to the incident light. If you zoomed in there, it's a combination of 2 materials. There's a thick aluminum material that doesn't absorb the light that kind of shorts out some of these lines. There's little thin exposed parts of titanium nitride that has high kinetic inductance and high resistivity to the incident far infrared radiation, and actually absorbs the light and changes and provides the kinetic inductance that changes the frequency of the resonator. The other 20% of this device, yeah.
I wanted to let you know there's about 5 minutes left for your talk and questions.
Okay, thank you very much. I'll wrap this up. So detector performance was great. This is, again, that same device as a function of input power. If you turn this into a noise equivalent power and look at kind of the flat spot where your signal will be, 1 hertz to kind of 1,000 hertz in this case, you can plot the noise equivalent power as a function of incident power. You get into 2 regimes here. This represents the effective detector noise floor. There's a little bit of noise in our noise measurements, but the noise floor is a little below 10 to the minus 16, we believe. And then when it starts to go up linearly or as a power law with the incident power radiation, this is where we get background limited performance. You can see it's well into this background limited performance into the Hawk loading levels that is shaded in gray here. So these were fully signal noise limited devices, which was the goal. So that was fantastic. And they did so with relatively high efficiency. We're still working on the final number. Here's pictures of some of the sample devices we made, including 512 device units packaged up here. 512 pixels was the fundamental unit for the Hawk potential, but you could imagine making a whole 150 millimeter diameter wafer full of these devices, in which case These are about 1.1 millimeter pitch. You would have over 5,000 pixels. We measured one of these large arrays of 500 devices, got very high yields and good quality factors with the resonators. And then finally, really quick, I just wanted to touch on the readouts that we developed an RFSoC, so radio frequency system on a chip. It's a new kind of FPGA electronics developed commercially and available commercially that will allow us to do readout efficiently and largely with commercial devices. This is just a demonstration that compared to a traditional readout, we got the same noise performance or same noise measurement. So we were not readout limited in any way by the new one. There's a lot of groups working on RFSoC based readout. I haven't seen anyone do a multi-tone noise measurement to this level. So this may be the first one, I'm not sure, but this was very great. This very important result that we got out of just this 6-month effort, which is fantastic. So we hit all of our goals for Hawk. We believe in the end, it would have provided about 10 times more mapping speed than the existing detectors, but it's too bad that didn't go forward. But we're looking for, more opportunities to apply this new technology. So I'll just wrap up with the summary here that we have an established feed-orn solution for the longer far infrared wavelengths. I'm working to push that up as far in far infrared that is practically possible for experiments that want to use that kind of technology. Then we have this brand new kind of direct absorption technology, high efficiency, very broadband devices that can be made polarization sensitive that we've recently published and was only briefly able to touch on here. So I'll end it there. Thank you very much.
All right, thanks, Jay. We have time for a couple questions. If you would like to raise your hand, we can call on you. Margaret.
Hey, very nice work. And yes, we're sad that Hawk Plus did not go forward, but this looks pretty cool. So Hawk Plus, of course, would have had a very, intense background because it's ambient temperature. What would you need to do something, at lower background, say in orbit?
Yeah,
what would you be changing in the kids?
Yeah, so unfortunately, yes, I'm sorry. Thank you for bringing that up. That's something I did skip over briefly here. So while I did show that these kind of kids are very large dynamic range without saturation, you still tune the design to the typical loading that you expect so that you have best performance around there. So the devices we developed, they already have built into them. There are ways that we could make them have higher responsivity or designed for lower background levels. So we can cut that down by a factor of a few, probably as is. And then there's a kind of more, this is a list of directions we can go to push that further for space-based low background and or spectrometers in space or otherwise that are very narrow bandwidth and be very low powers. One of the big ways to do is to reduce the volume of the active kinetic inductance providing material. Like I said, there's room in the current design. We could also easily get even more if it was a smaller or a more typical bandwidth than Hawk was, which was 6:1, which was a lot. You could do things like E-beam lithography to make smaller features and reduce the volume of your material that way. That's something we can do here, but just haven't had a application to really push hard on that yet. Or you could use micro lenses or other focusing elements to kind of bring the light down to a smaller footprint and thus reduce the volume of the active material, then, which pushes up its responsivity. We are also looking into different versions of the tinitride material, including reduces its transition temperature down to as low as 500 millikelvin. This both makes it more sensitive and reduces some residual 1/f that we see in tinitride-based devices. And then finally, you can get some more pie in the sky type stuff and think about putting these on a membrane, kind of like a TES is. And people have investigated this for phonon recycling. So as the Cooper pairs recombine to generate, that energy goes in the phonons, that if that's trapped where the sensitive parts of the device are, they can recombine and re-break a Cooper pair. And that just basically boosts the sensitivity by getting multiple breaks of pairs and superconductivity. So there are a lot of ways to make this more sensitive. And we believe that a combination of several of these could get us several orders of magnitude lower NEP. So as you saw, the device for Hawk, we're very appropriate, but we're on order 10 to the minus 16. And for space, we're going to want to get down to what I showed was recently demonstrated in Europe at closer to 10 to the minus 19 and below.
Thank you.
All right, so unfortunately, we have to move on to our next speaker, but we can carry on the discussion after the webinar offline. So our next speaker, I'd like to introduce Dr. Jed McKinney at UT Austin. He's a postdoctoral fellow at the University of Texas at Austin, where he works with Dr. Caitlin Casey and the Cosmos Web team on massive and distant galaxies. He is broadly interested in infrared observations of galaxies, with a focus on characterizing the cold gas and dust from which new stars form. Dr. McKinney recently defended his thesis at the University of Massachusetts Amherst, where he worked with Dr. Alexandra Pope on infrared emission line diagnostics of dusty star formation. Today, he'll be talking to us about efficient star formation in dusty galaxies. And I'll go ahead and hand the screen over to you, Jed, and I'll let you know when you have 5 minutes left.
Great, thanks so much, Nathan. Appreciate the introduction. Can everybody see my screen okay? Great. All right, cool. I'm excited to be here today, talking to you all about some work that I've recently done, characterizing star formation in dusty galaxies, both nearby and at high redshift. Some of this work was done during my thesis with Alex Pope at UMass, and also with Leah Armis and the rest of the goals team down at IPAC. And I'm sort of bringing some of this together with some new results to kind of give an overview of efficient dusty star formation. And I threw some dust emission detections that we have over HSD backgrounds on this title slide because I thought they were pretty, that'll come up later in the talk as well. All right, just to dive right in and give a little bit of brief scientific background. We know that at high redshift in the past, about 10 billion years ago or so, the volume average star formation in galaxies peaked in this so-called cosmic noon. Galaxies were forming more stars than ever before. And I really like this figure by Jorge Zavala that I'm showing on the right, which shows this star formation rate density separated between the dust obscured component in orange and the unobscured component in blue. And at and around the peak of the star formation rate density, you can clearly see this orange dust obscured component dominates. So most of the stars in the universe were being formed in these dusty galaxies. Moreover, within this dusty galaxy population, most of the stars were being formed in the biggest and brightest objects. And that's this top panel, which shows the fraction of the star formation rate density happening within luminous and ultraluminous infrared galaxies. So these are real monsters that are forming hundreds to thousands of solar masses of new stars each year. And I'm really interested in understanding what powers the star formation and how that contributes to the shape of the star formation rate density over cosmic time. Now, there are many competing theories about why cosmic noon occurred, why there was this peak in the star formation rate density, some related to the gas supply. But I wanted to talk about one in particular, which relies on this idea of the star formation efficiency. So surveys of star formation over time and surveys of the gas in galaxies over time don't quite agree with one another. And what I mean by that is if you look at the fuel for stars in galaxies that are forming those stars, you can't quite balance the budget. And that forces many of these large gas and dust surveys to invoke evolution in this quantity called the star formation efficiency. And that's really a galaxy's star formation rate over its available gas mass to form stars, and is an empirical term, but it's tied to our understanding of multi-scale physics that govern star formation. If a galaxy has a high efficiency, it's really good at forming new stars, and it would form more stars out of the same input gas mass. And what this compilation of literature results on the left evokes is that different teams come to disparate conclusions as to how important evolution in the star formation efficiency is in driving high star formation rates of galaxies in the past. And so one way to study this governing force in galaxy evolution is, of course, to make such observations of dust and gas in distant galaxies and try to really track this evolution precisely. I take a different approach, and I study the underlying physics regulating star formation in targeted galaxies to pick apart what what drives efficient star formation. And after all, as this figure on the right shows, we know and we find very efficient star formation in dusty galaxies, and particularly ones with high infrared surface densities. So ones that are forming lots of stars over compact areas. And so by studying such galaxies, we can understand potentially what helps drive the shape and the star formation rate density. Now, I mentioned that this is really a multi-scale physics problem because galaxies, of course, are consuming gas from the intergalactic medium. They're processing that gas to form new stars. Those stars exhibit feedback on their local environments, and that can help drive gas out of the galaxy as long as in addition to the outflows that are perhaps driven by nuclear activity in the form of supermassive black hole feedback. And this whole process is quite cyclical. But I wanted to just focus on this one component, really zooming into the physics on the scale of star-forming gas and understanding how gas cooling and gas heating regulate the efficiency of star formation. And in order to do that, I'm going to have to give some background on basically physical diagnostics of gas conditions in star-forming regions. So if you have a star-forming region or a photodissociation region, which is filled with molecular and atomic hydrogen, ionized carbon, and other metals, and small dust grains or PAHs, and that's near an OB star or star-forming region, far UV photons from those young stars will be absorbed by PAHs, which release photoelectrons, heating gas, and those collisionally excite far-infrared lines, which allow that gas to cool. And so the cycle of gas cooling and heating sort of plays out here as an energy channel through far UV photon absorption by PAHs, which are again are small dust grains, through the collisional heating of H and H2, and then the cooling through far infrared lines. And these are all observables in the mid-infrared window. So Spitzer was really great at taking mid-infrared spectra of these polycyclic aromatic hydrocarbons, these small dust grains, and the strength in these various broad absorption bands that you can see in this spectrum here on the bottom left can not only give you a sense for this heating component within the star-forming regions of galaxies, but various ratios help constrain the nature of the dust grains themselves, and in particular, the average ionization state and size distribution of the grain population. I mentioned that these far infrared lines are helping cool the gas. They're extracting energy out of the photodissociation region. And Herschel, for instance, was capable of measuring these in the nearby universe, and ALMA can be used to push these measurements to very high redshift. So by looking at these combined mid and far infrared diagnostics, you can get a handle on how gas heats and cools in galaxies. And so this was a major component of my thesis. And in particular, looking at these disparate diagnostics in dusty galaxies to understand, again, how those stars are forming. So I mentioned that Herschel was great at measuring far infrared lines, and it certainly did that for the Great Observatory's All-Sky LIRG survey. This is a flux limited survey of nearby luminous infrared galaxies, so dusty galaxies today. And then Spitzer took mid-infrared Spitzer spectra. And so a large portion of my thesis was working on GOLS galaxies with Lee Armis and the GOLS team at IPAC, and combining these mid and far infrared tracers to better understand how gas heats and cools. Okay. George Halou had a paper in 2001 that was an early look at this, and I'm showing that on the left panel here. This is the C2 luminosity measured by ESO relative to a broadband tracer of the PAH emission. And you can see this cooling to heating ratio traced by the far and mid-infrared lines is more or less constant as a function of IR color. And this suggests that as you go to hotter systems, perhaps hosting denser and more vigorous starbursts, that the average star-forming properties of those star-forming regions don't necessarily change, or at least the ones that are manifesting in the emergent intensities of these IR lines. And that's all to say that the gas might be heating and cooling similarly at different levels of dust-obscured star formation rates. So I was interested in looking at this in the GOLS sample, which hosts some of the vigorous and compact starbursts, dust-obscured starbursts that we see at high redshift. and seeing if the ISM conditions were changing in ways such that this cooling to heating ratio was the same or different. And so the figure on the right is showing a result of that effort, where you can see the C2 to PA luminosity and goals actually extends below these prior results by about an order of magnitude as you push to high infrared surface density. So as you're packing lots of star formation into smaller areas across the galaxy. And this is really interesting because this cooling to heating ratio is sensitive to interesting physics that, thinking back to that cartoon that I showed you, regulate the flow of energy from hot young stars into the molecular gas, and then that gas cooling. So it's a metric of those processes. But just looking at one far infrared line, here the C2 line, which is one of the more powerful ones in the far infrared, but that doesn't give you a whole complete census of how that star-forming gas is cooling. In particular, as you move to, for instance, more dense star-forming regions, more power channels out through the 63 micron oxygen line. So we added in other major cooling components, and that's what this figure is showing here. So the sum of major cooling lines in these star-forming regions normalized to the total power of the PAS, and we still find that at high infrared surface densities, a drop in this cooling to heating ratio. And these galaxies on this figure are from goals are colored by the strength of the radiation field impinging upon PDR surfaces to the neutral hydrogen density. Those are from PDR modeling. And what you can see is that when you get into this sort of inefficient, this low cooling to heating ratio regime at high infrared surface densities, the average ISM conditions are more extreme. And in particular, star-forming regions are seeing stronger radiation fields. And I just wanted to take a moment just to define what this empirical ratio of cooling to heating is trying to measure. And it's really a tracer of the photoelectric heating efficiency. And this is the fraction of energy that gets absorbed by PAH grains that gets transferred into the gas. So you can think back again to that cartoon that I showed. And just to clarify, low photoelectric efficiency, so low values along this y-axis correspond to lower heating rates. So basically you would get less power out of the cooling lines for fixed PAH intensity because the photoelectrons that are escaping those grains carry less energy out, and they are less efficient at sharing energy with the H and H2. So you're changing how H and H2 is warming in star-forming regions, star-forming gas around hot young stars. And so one of the physical scenarios that we think is contributing to these low cooling to heating ratios is that this photoelectric heating efficiency is becoming quite inefficient, which disrupts the flow of energy from the far UV photons into the H and H2 gas. And you can imagine that this might help keep that H and H2 cool, because the PAS themselves are inefficient heaters in this scenario. And as that gas is cooler, it emits less out of the C2 and other far infrared lines relative to the total strength of the PAS. And in particular, this could be tied to, this is really a small scale physical effect on the scale of star forming regions. And this would certainly be tied to the efficient processing of gas in galaxies. And so the next step, well, there are a few next steps, but the next step was to see if this effect manifested at high redshift, to see if some of these interesting scenarios at high infrared surface density, perhaps leading to the disruption in gas heating efficiencies, also manifested in the compact systems we're finding in the early universe. Okay, so I showed a GOLS galaxy previously. This is like a redshift 2 dusty galaxy that we detected in ALMA with ALMA and dust continuum. So we don't really spatially resolve the sources. We are making galaxy integrated measurements, but we have Spitzer spectra, which again are tracing the PAS, that heating component, and we're also looking at these far infrared lines measured by ALMA. I'm just going to skip right to the punchline. We were only able to detect the C2 line in 2 galaxies, but those 2 that we found are shown in red here against the GOLS galaxies as the black circles. And you can see they exhibit low cooling to heating ratios and are in this high infrared surface density regime where that catastrophic decline in the photoelectric heating efficiency was found amongst the GOLS galaxies. But of course, there's only 2 galaxies, and in fact, one of them is an upper limit. So I have an ALMA cycle 9 program to increase this sample to about 15 galaxies. But that's a costly program. It takes over 40 hours because of the atmospheric transmission in bands 9 and 10. And so to really revolutionize our understanding of these far infrared lines and how they relate to their host galaxies and the star forming conditions within them, particularly at high redshift, we're really going to need a space-based far infrared telescope. For one thing, far infrared lines like C2 are really inaccessible currently between redshifts of 0.2 to 1. And as I said, this program to increase the sample size to 15 is quite costly. And if you're interested in a far infrared space-based telescope or advocating for one, I'd encourage you to register for the NASA Precursor Science Workshop, which is being held October 11th to October 13th, if I don't have my dates mixed up. And this is going to help aid the discussion that goes into NASA's deciding on a probe class mission telescope. And if you have an idea about a science gap that needs to be filled or could be filled that would aid in the design of such an instrument, you can also support or submit those ideas through a Google form as well. And hopefully these QR codes work. So you should be able to scan them with your phone if you want to right now, or take a screenshot and use them later, or we'll circulate PDFs of these slides too. Okay, but I'm going to pivot gears here because I introduced this talk as talking about efficient dusty star formation, but so far I've only mentioned interesting physical scenarios that sort of underlie our notion of how stars form. But I wanted to pivot more into discussing observations of the dust mass of distant galaxies and using those to anchor estimates of the star formation efficiency in individual galaxies. And while we will need a space-based telescope to do large statistical surveys of these far infrared lines to unpack the interesting physics in star forming regions at high Z, we can, taking the lesson that many of these empirical trends related to the mid and far infrared lines really hinge on the infrared surface density, in that as you push to the high infrared surface density regime, the cooling to heating changes in interesting ways, as I just mentioned. So foregoing efforts into observing many far infrared lines with, for instance, ALMA, those are coming up. But in the meantime, we can look at actually the star formation efficiency of individual galaxies. And this is leading to some recent work that I've done using an ALMA archival program. But it was all to answer this question of, do dusty galaxies form their stars more efficiently in this high infrared surface density window where we're seeing the cooling to heating physics change in these dusty galaxies? And would this trend change or not with redshift? We know, for instance, that in the local universe from Gold's galaxies, that as you push to the high infrared surface densities, these galaxies are progressively at greater distances above the main sequence. They're more starbursty. They're less typical in terms of the typical star-forming galaxy. But that's not necessarily the case at redshift 2. So studying these compact dusty systems and how they're forming their stars is more representative of more typical star-forming conditions in the early universe. There was some work that looked into this previously. This figure from Alison Kirkpatrick's paper in 2017, shown on the bottom right, shows the star formation efficiency traced by the total infrared luminosity relative to the dust mass as a function of the overall diameter of the galaxies. And it's really there's not a conclusive trend here, but that's in part due to an inconsistent use, or rather different tracers of the star formation, the sizes of the galaxies being used, some relying on different lines and different continuum tracers. And the great thing about far infrared observations with dust continuum is that you can use almost spatial resolution to pick apart the size consistently, but you're also measuring emission at long wavelengths, which is good for measuring their dust masses, again, to constrain the overall star formation efficiency. So we did that. We measured IR sizes and dust masses in dusty galaxies. We did the ALMA archival work was done to get the redshift 2 component, but we also had rich data at redshift 0 to test for trends with redshift. And some of the results of this work are shown here. I'm just showing some of the archival observations of these dusty galaxies. And I just want to note that we selected this sample on the existence of mid-infrared spectra because that lets you decompose between star formation and dust obscured AGN. So we didn't select out we didn't select out dust obscured AGN. Rather, we included all these galaxies in our sample, but we're able to correct for the relative contribution of the AGN to the total infrared emission. So this figure nicely summarizes the results of this work. So this is showing the effective radius along the y-axis measured at in the infrared as a function of the dust mass that we measure consistently across all the different samples. The Redshift 2 sources that we detected using the ELMA archive are shown in pink. We got about 19 of them. These were mostly in good self, or all were in good self. The GOLS galaxies are shown in blue, and the Kingfish and galaxies from the Kingfish survey, which are more like normal, typical star-forming galaxies, are shown in gray. And what's interesting too is that the LERGs and ULERGs, these massive star-forming factories, these are GOLS in the Redshift 2 galaxies. Those overlap with sort of the extreme compact galaxies from illustrious TNG 50. And so the simulations are capable of reproducing the parameter space and IR size and dust mass that we're finding in these dusty galaxies. And bringing this together, sort of back to the original question, what we find is a redshift independent trend towards efficient star formation at high infrared surface densities. And that's what this figure is showing, using the infrared luminosity and dust mass to trace the star formation efficiency on the y-axis, shown against the IR surface density along the x-axis. And this spans about 4.5 orders of magnitude as you push to the high infrared surface densities and GOLS, and those at Redshift 2, these galaxies are forming their stars more efficiently. And the trend that we find is slightly steeper, but more or less consistent with previous works that have looked at other handfuls of dusty galaxies under different selection criteria. There's been a lot of work recently using ALMA to spatially resolve the sizes of distant and dusty galaxies. And what this figure shows from Seiji Fujimoto's 2017 work is that as you push to higher redshift, the average IR size of galaxies is decreasing. And so any of these trends that we're finding sort of in this high infrared surface density regime may be more present at earlier times as surface densities increase. And again, just to mention it one more time, this is the regime where we're seeing changes in these cooling to heating line ratios related to interesting physics on the scale of star forming regions. And so by using these mid-infrared tracers and far infrared diagnostics, we can begin to unpack again what might be behind this efficient star formation. And while we'll have to wait for some ALMA data to do that more statistically using the C2 line, we have the Spitzer spectra detections of the PAS. And just looking at those really briefly, here you see the PAH luminosity over the infrared luminosity relative to the IR surface density. The GOLS galaxies, again, are colored by the radiation field strength and neutral hydrogen density from PDR modeling. And we find a PAH deficit that's sort of consistent between the low and high redshift sample. And as you push to high infrared surface densities, the fractional strength of the PA line relative to total LIR decreases. This is reminiscent of the C+ and other far infrared line deficits that are well characterized at Redshift 0, at Redshift 5. It's also consistent with photometric IR8 over LIR trends used to approximate the emission from PAS as well. So this suggests that some of the interesting PDR physics that we see at place at Redshift 0 might also be manifesting in the Redshift 2 galaxy population. Okay. So just to summarize some key takeaways, we find luminous infrared galaxies have low cooling to heating ratios at low and high redshift. This is more pronounced in compact dusty star-forming galaxies and might really depend on the properties of small dust grains and how those govern gas heating and cooling in star-forming regions. We find efficient star formation towards high infrared surface densities. And because high infrared surface densities seem to be more common at early times, this might help drive efficient star formation and supporting the peak of the star formation rate density. Okay, so that was a mouthful, but that summarizes some of the work that I did for my thesis and also some recent work. I'm gonna just mention that one of the reasons why I came to UT was to work with the Cosmos Webb program, which is the largest James Webb program in cycle 1. That's going to be surveying the Cosmos field with NIRCam and a smaller subset with MIRI. And with this, we're going to be able to study star formation in massive galaxies in the early universe. And in particular, using the really great spatial resolution of James Webb at these wavelengths, look at the optical and near-infrared morphologies to characterize compact star formation, not only at cosmic noon, but beyond and into the epoch of reionization. So I'm really excited for some of the science that's going to come with this program. We're going to get our first data in December. I also wanted to take a second to advertise some upcoming webinar talks that touch on some of the mid-infrared diagnostics that I mentioned earlier. Vivian Yu is giving a webinar talk on December 5th, and this is related to her recent James Webb paper, and you can see spatially resolved iron 2 emission from that as well. And I encourage you to not only check out the paper on arXiv, but also attend the talk, which will be quite great. And similarly, Thomas Lai is giving a webinar talk on November 7th. And again, that's related to this James Webb paper looking at spatially resolved PAH emission in the nuclear star forming ring of NGC 7469. You can see that in the bottom right. You can also check out the arXiv link to that paper as well. So it's an exciting time for mid-infrared observations with James Webb, and the future of far infrared observations of distant galaxies is also quite exciting. And again, I just wanted to encourage you to reach out to me, particularly if you're a junior scientist and you're interested in getting involved with some of these NASA mission design discussions. It's a process that I recently went through and getting up to speed with, and I'd be happy to chat and pass along some of the stuff that I've learned. But nevertheless, I'll end my talk there. Thanks for being here, and I'll take any questions.
All right, thanks, Jed. Do we have any questions? You can go ahead and raise your hand in the Zoom window. Irene.
Hi, Jed. Very nice results. I had a question about your ALMA work, the one that you were showing IR luminosity to dust masses. Are you worried that those two quantities might be degenerate, or are you getting them from different data points? Maybe I misunderstood.
No, that's a really good point. So the question is about how do we measure infrared luminosities? How do we measure dust masses? So the dust mass observations are tied to the archival data, which is mostly at 1.1, 1.2 millimeters. We have Herschel 250, 350, 500 micron observations for these galaxies as well, which help constrain the cold dust. So we have, and in principle, the infrared luminosities were calculated without including the dust points on the SED. So they are separate.
Thank you.
Thanks for that question. That's a good one.
All right, any other questions? All right, well, I'd like to thank our speakers again. I'll go ahead and put up a slide just to advertise our future webinars. And we are looking for speakers. So if you would like to present or know a colleague that may be interested in presenting at one of our upcoming webinars, please get in contact with us. If you'd like to receive notifications about the webinars or other events, please go ahead and join our mailing list. And you can find recordings and more information about the webinars on our website. And with that, unless there are any other questions, thank you all for coming, and we'll see you on Monday, November 7th.